Hi, welcome to Knowledge Quest 14, Helical Coil Spring Design. This is our last knowledge quest of the quarter, and I think it's an interesting knowledge quest to end on because in my mind it is authentic, meaning it is like a design problem you might encounter in real life. You're going to have a lot of different design parameters to meet, and at first glance, not a lot of information to get you started. So our design scenario, we have a musical wire helical compression spring needed to support a 20-pound load after being compressed 2 inches. Because of assembly considerations, the solid height cannot exceed 1 inch and the free length can't be more than 4 inches. Design the spring. So first question, where do you start? If you wanted to, for example, calculate the ultimate tensile strength, you would need to know the wire diameter, and that's not given. If you wanted to figure out the stress correction factor, KB, you would have to know the index of coil curvature, but you don't have the mean spring diameter or the wire diameter, so you couldn't right off the bat calculate C. So in this situation and in lots of other design situations in engineering, you're going to come across at least some recommended design considerations to initiate a design. So for springs, there are 4 that we're going to use. So these are the 4 recommended design considerations to help you begin your spring design. So the coil curvature can be one of the first design considerations. So at C of less than 4, the spring is difficult to manufacture and you might run into some surface cracking issues. At C greater than 12, the spring is prone to buckling and it also tangles easily when handled in bulk. So number of active coils. I'm not sure where this one came from. I think this is more for like a freestanding spring. You want to keep the number of active coils between 3 and 15 because I am pretty sure that my pogo stick from when I was a kid definitely had more than 15 active coils, but you can see in this pogo stick that it's also supported by an internal rod. But in general terms, we're keeping the number of active coils between 3 and 15. In terms of factor of safety, I think a factor of safety of at least 1.2 is good general advice, but you might want a higher factor of safety for critical applications. And note that NS is the factor of safety at closure, so the spring solid height. And this is when the spring is subjected to the highest force, and hence torsional shear stress is at its greatest point. So this Z parameter is a fractional overrun to closure. And what it's actually doing is trying to limit the maximum operating force to 87.5% of the force that would bring the spring to closure where all of the coils are touching. And this is because springs begin to act non-linearly when their coils begin to touch. So Fs is the force that would cause the spring to compress so that all the coils are touching. And again, we want F max to be less than that because we don't want to have this nonlinear behavior. Okay, so you're going to use these recommended design considerations to generate a table, and this is what you're going to be doing for your homework. So you're going to take the design considerations that I just talked about, along with some initial decisions about the material choice to generate a table. So the first thing you need to choose, at least for this first iteration of a design, is the type of wire. So hard-drawn steel wire is usually the first choice because it has a low cost. And then you're going to choose a range of wire diameters to analyze. So in my table, I have wire diameter D, 0.063, 0.067, 0.071, etc., and that is in inches. So you're going to generate a table of parameters just like this one, and it's going to have wire diameter, mean coil diameter, index of coil curvature, outer diameter, inner diameter, number of active coils, solid length, free length, critical free length to avoid buckling, and the factor of safety. So you'll see these are all listed in this first column. And then in this table, I already have the factor of safety of 1.2 and the fractional overrun to closure, Z, of 0.15. They've already been taken into account. So then from your problem statement and this table that you've generated, you're going to identify acceptable diameters. So right off the bat, if we know that C has to be between 4 and 12, only wire diameters of 0.063 and 0.085 would be acceptable. And then for number of active coils, remember that has to be between 3 and 15. So wire diameters between 0.075 and 0.095, and maybe a little bit higher than that, would be sufficient. So far, our overlap is 0.075, 0.08, and 0.085. Those wire diameters would work based on the criteria of the coil curvature and the number of active coils being within our accepted range. But you will have other design parameters, which could include the inner diameter, the outer diameter, the solid length, and the free length. So if we go back to our example, which I will show you how to do in my analysis tool, the solid height cannot exceed 1 inch and the free length can't be more than 4 inches. So these would be 2 additional parameters, and you'd use the table to identify wire diameters that would meet these parameters. So the only 2 parameters we haven't talked about are alpha and beta. So alpha is just the torsional yield strength divided by the factor of safety. Beta is 8 times 1 plus the fractional overrun to closure times F max divided by pi d squared, where d is the wire diameter. And then both of these parameters allow you to calculate C, which is really useful. So it looks like a quadratic equation in C, which it actually is. And it actually just comes from a rearranging of an equation we've already learned. Tau equals kb times 8fs d over pi d cubed, where tau is the torsional yield strength divided by the factor of safety at closure. So I won't go into the derivation of it. It's in the book. What you need to do is put alpha and beta into your tool to be able to calculate the index of coil curvature in your table. And then you should have a completed table. So back to our example. I'm going to step you through this problem in my analysis tool now. So here we are in my analysis tool. I have a section of preliminary decisions. So A and M are a function of the material. So we have a musical wire spring. So A and M are from table 10.4. The percent of the ultimate tensile strength for the torsional yield strength I picked as 0.45 based on recommendations in table 10.5 and also appears in table 10.6. Modulus of rigidity is from table 10.5, so we have music wire. For my first assumption, I'm going to go with a wire diameter range of 0.064 to 0.125. So G in MPSI is 11.75. So again, got to keep track of your units. So I did 11.75 e to the 6th. So this is entered in PSI. Factor of safety at closure, 1.2. That's the minimum. It's fractional overrun to closure, which I guess is technically xi, not z. So whatever, xi. I said it's 0.15. F max 20 pounds. This comes from the problem statement. The spring is supposed to support 20 pounds after being compressed 2 inches. So that 2 inches is our Y max. And based on our F max and our Y max, we get our spring constant K. So the table shows a range of diameters, 0.063 to 0.095. SUT is the first calculation. So I'm going to show you a little Excel trick. You may already know it. But SUT, remember the formula is A over D to the M. D is the only thing that's going to change as we move along the row, and we want to hold A and M constant. So how to do that in Excel is to use dollar signs. So if you look at my first formula, $C, $30, that's A. So that's going to hold A constant as we move along the row for D, divided by D, which of course we want to change to the exponent M. So D to the $C, $31, and that is the cell corresponding to M. Torsional yield strength is 45% of the ultimate tensile strength. Again, I'm using dollar sign, so we have the ultimate tensile strength, C42, which is going to change as we move across, times $C, $32, which corresponds to cell C32, which is held constant. We already talked about alpha and beta, so you got to put those in, and that's going to give you your C. And what we can do right now is just highlight the range of acceptable C values. So C can be in between 4 and 12. The mean coil diameter, you get that from the index of coil curvature times the wire diameter. KB is 4C plus 2 divided by 4C minus 3. The outer diameter is the mean coil diameter plus 1 wire diameter. And then the inner coil diameter is the mean coil diameter minus 1 wire diameter. So where did the number of active coils come from? It came from this formula here. So we have K, wire diameter, G, mean coil diameter. So it's just rearranging and solving for the number of active coils. So we can fill some of these cells in because we only want active coil diameters between 3 and 15. So that would be an acceptable range. So the number of total coils is the number of active coils plus 2, and that is just based on my choice that we're going to go with squared ends. So now you have this range of solid lengths and a range of free lengths. So the problem statement says the solid height cannot exceed 1 inch. So here would be our choices. And the free length can't be more than 4 inches. Now we're looking for where the acceptable cells overlap. So 0.08 inch wire diameter and 0.085 inch wire diameter would both meet all 4 criteria. I'm assuming a 0.08 inch wire diameter would be a little bit cheaper than a 0.085 inch because it's a smaller diameter. So that would probably be your choice. All right, thanks for watching. Bye.